Hello, and welcome to our webinar, Solving Tooling Challenges with Metal 3D Printing, a New Approach. I'm Ian Wright, Senior Editor for 3D Printing at Engineering.com. Thanks for joining us today. So we've got a couple of housekeeping notes just before we get started. First, in the webinar platform, you'll see boxes for the presentation slides, speakers, chat, and so on. These can be moved and resized at your preference. A couple of boxes to note in particular: the resources box has today's presentation slides, and the Q&A box is where you can ask questions. So we will have a Q&A session at the end of the webinar, but feel free to ask your questions as they come to you, including on demand. That's right, if you're watching this webinar on demand, you can still submit your questions and our presenters will get back to you. A recording of this webinar will be available on demand at engineering.com. And if you happen to run into any technical issues during our webinar, the first thing you should try is refreshing your browser, and if the problem persists, reach out to us through the Q&A box. So thanks to Mantle and to Heyco for sponsoring this webinar. And now I'd like to introduce today's speakers. Ethan Raito is Director of Marketing at Mantle, and Bill Coyle is Director of Engineering at Heyco Products. Ethan has extensive experience in technical marketing for design and manufacturing products. He previously ran the technical marketing team at Desktop Metal, and before that he was part of the rapid prototyping team at MIT Lincoln Laboratory, where he worked on the laser communication system for NASA's Orion mission. Bill has been with Heyco Products for 30 years and currently leads its engineering team. He's worked across all aspects of Heyco, including product development and manufacturing. Heyco Products has over 30 injection molding presses and a complete tool room. Bill led the efforts to implement modular toolmaking and molding capabilities at Heyco. And without further ado, I'll turn the presentation over to them.
Awesome. Thanks for the introduction there, Ian, and making us sound so great. As Ian said, today we're going to be talking about solving tooling challenges with metal 3D printing technology. Both Bill Coyle is on the line here, as well as myself. Just a quick agenda of what we're going to be covering today. We'll be talking quickly about a quick introduction to Heyco and Mantle and Bill and I, which Ian already did a great job of teeing up. We'll talk about Heyco and 3D printing, talk about Heyco and their tooling operations and manufacturing operations. We'll do a quick introduction to Mantle and talk about how our metal 3D printing technology for toolmaking actually works. And then we'll look at a bunch of different case studies from Heyco and a few others of how people are actually implementing this technology to reduce tooling lead times, costs, labor, etc. Won't spend too much time here on the introduction to myself because Ian did such a great job here, but I've been at Mantle for a little over 2 years, really since the launch at IMTS 2 years ago. At a large trade show there. I have a lot of experience in technical marketing. I'm actually an ex-engineer turned marketer here. Have a BS and a master's in engineering, but I've spent a lot of time on the technical marketing side and the manufacturing side specifically, really trying to understand use cases and applications and educate people on all the exciting things that are happening in the manufacturing world. If you don't know much about Mantle, Mantle is a metal 3D printing company, but we're a little bit unique in that we are specifically designed our system for tooling. It's the only application we do, and mostly that means injection mold tooling, and that's mostly what we're going to be talking about today. The goal of Mantle is to really help our customers automate their toolmaking processes, and we do that by printing precision mold components that really have unmatched accuracy, surface finish, and tool steel performance. Not sure how well this will come across on the camera here, but I have a couple inserts with me today that I'll be showing. I think Bill may have some too, but really just unprecedented accuracy and surface finish that enables these tools to be used for molding, which then allows you to eliminate most of the time and cost of the really, really time-consuming and expensive toolmaking operations like rough milling and specifically EDM. We're going to talk a lot today about how our technology allows you to remove sinker EDM on deep ribs and components like that. We're going to talk more about Mantle later on, but I'll turn things over to Bill here to talk a little bit about Heyco and himself.
Hello, how's everybody doing? Thank you for the great introduction. I really don't have to talk too much about myself. You guys covered everything pretty well for me. Heyco overall is a metal stamper and plastic injection molder, as well as we do assembly of components that we manufacture for final sale. So that's kind of my what we do, and I've got extensive experience. As said, I've been here for over 30 years and been doing a lot of design work and part design, as well as tool and manufacturing design. So move forward with that. Heyco's a 98-year-old business. We were started in 1926. We originally started by stamping children's toys out of brass. And then when the war effort hit, Heyco was tasked to start making the electrical components for the vehicles. And we've been in that business ever since. We've stayed in the electrical market. We started in the stamping, and then we evolved into molding, and we are a wire management, wire protection, and wire termination company. We're experts in design and manufacturing of molds, molded wire protection products, and stamped electrical components. We offer design, prototyping, high volume manufacturing, custom solutions, as well as deliver the best to our products to our customers. We have a 30+ injection molding presses ranging from 55 tons to 310 tons. We have progressive metal stamping ranging from 25 tons to 60 tons. And then we have 4-slide metal forming capabilities, then packaging and automation, assembly and automation. We have a full in-house tool room, 15+ toolmakers, CNC grinding, wire EDM, sinker EDM, lathes, conventional mills, CNC mills. And we have the capabilities of making all of our own tooling internally. We just don't have the full resources to make all of that tooling internally. So that's always a challenge for anybody who does tooling, design, and manufacturing. So other challenges to tooling, design, and manufacturing is because we don't have the capacity to do all of our tools in-house, we obviously have to look to outside sources, and those outside sources have longer lead times, higher costs. Prototype or low volume parts can be challenging due to lead time and cost. And then it's, of course, hard to hire those experienced toolmakers, hard to find those experienced toolmakers so that you have the capabilities to be vertically integrated. It limits our product development speed and any changes that have to happen during the process of R&D. We've actually been a pretty quick adopter of technology. We've had metal 3D printing in the past and still have that original machine. It's a sintered powdered metal, and we use it mostly now for fixturing, conformal cooling, and casting replacements, because when we were trying to do the molded cavities with this machine, it was a lot of secondary work. It didn't have the surface finishes we needed to be able to mold directly out of the cavities. So we ended up doing all the EDM work that we would do to a normal conventional block of steel. So it didn't always make sense. But having that since 2006, we realized the value of 3D printing for tooling and began investigating and constantly investigate new technologies. We were introduced to mantle early in 23, and we integrated a mantle machine into our building in December of 23. We were impressed with the surface finishes and the tolerancing. We were able to actually print, and I have here, this is I hope you guys can see this. I don't know how well it'll come through on the camera, but this is the very first insert that we printed as a sample off of the mantle press. And it was a replacement for an arrow insert on a small wire management part. So they prototyped it for us. We started injecting it. All we had to do was square the block up, tap the holes, put the ejector pin holes in, and then put it in the frame. So we were able to very quickly trial it and look at the development through the mantle system. So far, our experience is that mantle is saving us 75 to 90, or is printing steel that is 75 to 95% complete with minimal user interaction. The inserts require squaring, finish tapping, ejector holes, pinholes, that kind of stuff. Very minor toolmaker time. We've seen a dramatic reduction in tool lead time, producing these H13 tooling in as little as a week. We're able to produce tooling faster without the use of as many toolmakers or as much toolmaker time. We are reducing our R&D and development time to get parts to market faster. Tooling is a critical part for Heyco. So mantle enables us to be more vertically integrated and strategic over our tooling suppliers, as well as maintain our R&D and keep moving projects forward quickly so that we don't have any issues.
Awesome. Thanks, Bill. So I'll talk a little bit now about what makes Mantle's technology unique and how it really helps get you to that 75 to 95% complete stage with the printing process. So the conventional toolmaking process, like you're seeing here on the screen, requires a lot of steps. And each one of these steps adds cost and adds lead time to your build. All of them are required and all of them are very unique in that they all serve a certain point, but these tools are very, very complex and very, very costly and expensive to build just because of how much is required and goes into them. As Bill already alluded to with the Mantle process, we are taking most of the steps out of the process. You're going to an insert that is 75, 85, maybe 95% complete because you're removing all of the steps involved just by hitting print. And you just have to do a little bit of final finishing, which is generally just squaring the block via grinding and finishing some ejector pins just because of how precise those components are. So removing most of the time and cost associated with a tool build by simply just printing those components. As Bill also alluded, the printer's just going to be working, so it really reduces the amount of toolmaker time involved in a build as well. So you can really take advantage of the toolmakers you do have, just because it's so hard to find toolmakers right now that increasing toolroom capacity by hiring generally is not an option as much as people may want to. It's just so hard to find toolmakers today. So this system allows you to increase capacity. It's a relatively unique process that's very different than other metal 3D printing technologies. It involves a hybrid approach of printing and shaping and then a secondary step in sintering. And I'll kind of walk through how this process works because it's very different than other metal 3D printing technologies and even other 3D printing technologies you may have seen. We actually print a metal paste. This paste is similar to a toothpaste that hopefully we were all using this morning. It's a flowable paste, it's viscous. And what that paste actually is a combination of metal powder, so metal particles, metal powder, mixed with some binder like a glue, and then a solvent. We mix all of this together into a slurry, and this actually comes in a cartridge. So what we're printing is actually inside of a cartridge. The material here is viscous. You could flow it, you could squeeze it out of a syringe, but it's that combination, that slurry of metal powder mixed with binder and solvent. The first step of our process is to print. So we are not actually heating this material. It's viscous enough that it can just be extruded with a pump. And we're just pushing it through an extruder needle, essentially, to lay down material. In this stage, the material is very flowable. There's no loose metal powder involved because it's all inside of the slurry. And we're just sort of placing this where we want it to go. After we lay down our material, we come through and we dry. This is done just with heat as well as with a fan. And what we're actually doing here is we're removing the solvent out of the material. So we started with that paste that was that metal powder, that solvent, and that binder. Now we're going to heat it and remove the solvent. The truth here is that the solvent's really only required to allow it to flow, to be viscous enough that it can be extruded. After we dry it, it's kind of densified a little bit, and it's more like a dense foam now. So we've gone from our toothpaste to sort of a foam, which is really critical for us because now we're able to machine it. So we actually build our printer inside of a robo-drill style CNC. So it's a CNC that we retrofit to print our paste material, because every single layer we are printing, drying, and machining. So every single layer this is happening, and during that machining step, we're refining the surface finish, or maybe adding in some features that we weren't able to print because of the nozzle size, or the layer height. And that's really what enables us to get this really excellent surface finish, some really, really tiny features and some really, really crisp edges and things like that that are absolutely essential for a tooling application. So every single layer, this process is repeating to build your part up layer by layer by printing, drying, machining, printing, drying, machining. I have a quick video here just to hopefully get this point across a little further, where you can actually see this taking place. I know it takes a second to pop up here, but you can see that extrusion of the paste here. Just extruding it out relatively quickly, coming through and drying that with some heat just to remove that solvent. And then using standard CNC techniques and tools, we go through and we refine the shape, improve that surface finish, and add any feature details that weren't able to be printed. So that's happening every single layer. And of course, this repeats to build up your part. All automated. It's going to work over the weekend, work overnight, etc. You just have to set it up and let it run to get your insert complete. One thing I wanted to point out, is pretty interesting about this, is that since we are machining essentially a dense foam and we're machining layer by layer, we're able to use some really, really small cutting tools. So we're actually just using standard cutting tools. There's a turret inside of the machine, so we can use a variety of different tools at once. But we're able to use tools as small as a 10th thou and a 6th thou ball end mill. These enable really, really crisp feature details and really, really, really sharp small features to be produced here. If you were to ask, your machinist to go and machine a wrought block of hardened tool steel with a 6th thou ball end mill, they would say no thank you, or good luck doing anything with that. Since our material is in a softened state at this point, it's no problem to do. Just wanted to re-emphasize this point. So every single layer is being milled here, and I oversimplified it a little bit in my demonstration here, but actually every 10 layers we're going through and doing the contour milling. So you can see after 10 layers have been printed, we go through and do that contour milling, and this really enables us to do these really, really deep ribs, because we're printing and machining, printing and machining, printing and machining, printing and machining to get these really, really deep ribs printed that you would never be able to machine on a wrought piece of tool steel, just because of the aspect ratios are too extreme, which is very common in injection mold tools, and that's why they use so much sinker EDM. Generally, when we're talking to people about sinker EDM process, it's the number one thing they're trying to eliminate, just because of all of the cost and time associated with that. And we're going to talk a lot about that later when we start looking at applications, just to see how we can eliminate that. But just an example here of, this was a hard picture to take of just how small these tools can get. It's pretty incredible that we're able to use them to actually machine some features. After all the printing is complete, we go into a sintering process. If you're familiar with metal injection molding or other powdered metal processes, this is a sinter process. You put a bunch of parts in the furnace at once. It heats up and removes that binder out of the part. It's actually just boiling it out of the part. Then you get up to a temperature where the material is almost at its melting point, and it sinters these powdered metal components together. We do shrink about 9% in this process. That's about half of what you would see in a powdered metal or other sinter-based technologies. But we're able to predict that relatively accurately to achieve that plus or minus a thou per inch. This is, of course, where we lose our tolerance. It's great that we can machine parts to be as precise as we can get with a machining tolerance, but how closely can we predict that shrink is the challenge. But even with that, we're able to get plus or minus a thou per inch here. A little bit harder to get a camera into a high temperature sintering furnace that gets up to 1400 degrees Celsius. But a quick animation here just to see, it's really just it's almost like an oven, right? You stick the part in there, you hit start, and it's going to come out as a dense, strong metal part, as you can probably hear there. Toolmakers would probably not be happy that I'm smacking these inserts together, but it's pretty incredible that you go from a metal paste, like a toothpaste, into a 40 plus Rockwell H13 insert with just a couple of automated steps here. As I mentioned, we go into this batch furnace, automated cycles, and what comes out is tool steel, very, very stable material, which is really, really important. So if you do need to do any post-processing, the material stays very flat and very stable. I never like to talk too much about the technology without getting into some of the applications, because realistically, there's a lot of companies out there that have really fancy and impressive printing technologies. But what actually matters is that it's saving time and saving money for our customers. Constantly seeing our customers 50% plus lead time savings, 50% plus cost savings. And one thing that we didn't anticipate at first is how much toolmaker time they value eliminating, because toolmakers are in such short supply that they need to really take advantage of what their toolmakers are capable of doing. So if they can go from 100 hours on a project just to 10 hours of toolmaker time, that's really valuable for them in order to increase capacity. And we'll look at a bunch of examples later, but I just wanted to show a couple of here that we will talk more about later on. In terms of tool steels, two real materials available today: H13 tool steel, which is known as really the workhorse of tooling materials for high volume. It comes out of our process at a 42 HRC, but can be heat treated over 50 if you need to. And then a 420 stainless steel, which is a really ideal material for corrosion, molding environments, conformal cooling, medical device, etc. One thing that's always really, really important to our customers and top of mind with this technology is, can I do my traditional toolmaking operations to this if I need to? As we mentioned, mantle's going to get you 75, 85, 95% of the way there, but almost always there's some grinding involved to fit it into the mold base, finish your ejector pins, maybe you need to polish it, etc. All of these materials are compatible. You can polish it up to an A2. You can do your EDM if you need to, wire, sinker, etc. Even texture or weld. I don't know, Bill, if there's been any feedback from the Heyco team on how finishing mantle inserts have been, but generally we hear it's pretty great.
Yeah, so far we've put it through its paces, and we've tried just about everything to make sure is so we know where we stand, and it machines very similar to a standard metal block that you would buy from the supplier. Polishing is the same. We've sent it out to weld. It welds fine. We don't really do any chemical etching or texturing, so we haven't done that. But as far as any conventional means of working the metal, we haven't seen any real difference to a standard H13 or S7.
Awesome. Yeah, and that was really the goal here, is get you something that's 75% of the way there without having to change, your whole operation around or anything like that. The number one question we always get is, oh, great, you can 3D print an insert. It must be for prototyping, or maybe you can shoot 100 shots or something like that. Tessie Plastics, a really large injection molder in the US here, wanted to put these to the test. They took 2 mantle inserts actually, and they put them into a 32 cavity tool. This is actually a deodorant stick, so it goes into your bottom of the screw for your deodorant to advance it up. They have a big 32 cavity tool here where they're making tens of millions of these a year. They replaced 2 of these cores with mantle printed cores, and they've been running over 1.65 million cycles, and they're still running with no signs of unexpected wear. They actually have some S7 shutoffs coming on it where they would have expected to see a lot of wear, but they didn't. These are still running, so we're constantly having to ask them to update this number here on these slides, but it's just a good kind of our golden example of the durability. That's not just prototyping. Of course, you can use it for that, but these are H13. They can run millions of cycles if they need to. And in this scenario, they were still able to produce these inserts weeks faster than they could have produced them conventionally. Just a good example of the durability that's possible. So we've talked a little about Heyco and how they're using this technology and their manufacturing operations. Hopefully you have a better understanding of how the technology actually works. But I think what's most important is what are the actual results? How is this adding value? How is this helping Heyco get to market faster, reduce tooling lead times, et cetera? And we have a bunch of examples here that Bill can walk through of different scenarios where they've used the Mantle's technology to do exactly that.
So this was the block that I actually showed you initially. That was the first block that we had printed on the Mantle machine, and I've now pulled it out of the tool just so you guys can see it. That part has run probably about 1.5 million shots already on that block without any real issues. So that it's been very helpful to do that, and we were able to. We actually used the Mantle machine to. So we produced a block. Obviously, this is the savings that we would have seen if we had done it conventionally. We would have had to rough mill the block, prepare it, design and program and machine all the electrodes, drill and tap all the holes, send it out to heat treat, then sink EDM, wire EDM the ejector pins, burn the gates. Whereas with the Mantle, it was printed and sintered. We squared the inserts, tapped the holes, wired the ejector pins, and burned the gates, and it was ready to go. We've actually even experimented a little bit with certain gates shapes that we can actually print right into the machine and just clean them up. But that's that's all experimental at this point. Mantle does recommend burning your gates still, but for the best finish. However, as you get this technology, you can do with it as you see fit and really experiment. And they're great. They're a great partner to help you out when you're doing the experimentation and give you real good advice. We then use the Mantle machine to actually build an entire second set of cavities so that we could run more cavitation during production runs. And it saved us a couple of weeks and probably about 60% of the overall cost of producing it conventionally. This is a 3D printed thread insert on this slide. So what we did is we had a prototype tool that we were running, and we needed to change the thread detail because the thread detail came out way too small once the plastic shrinkage was into the part, and more so than we expected. So we took the insert and we milled the pocket, and we printed the 3D threads, or printed the threads on the Mantle machine, and they came out nice and crisp. We didn't need to do any real finishing, and I think that's actually on the next slide. So yeah, so the thread detail was crisp. All we did was blast them, tap the holes, and put it into the cavity. The MPT threads came out functional. They gauged properly. They sealed properly in a tapped hole, and our overall savings was probably 2 weeks, if not more. Another thing that we did, this was again for, we do use the mantle for a lot for prototyping as well as small inserts right now for production. Again, we're just getting into what capabilities we have with it and what's the best fit, but this is a big help for our prototyping and R&D and moving projects forward quickly. So this is a copper crimp ring. We needed to be able to properly crimp the wire and retain the copper crimp ring onto the wire for a good ground on the shielding. So we developed the new product. We're in process of developing a completely new product that isn't shown here, the full assembly, but this is one component that was necessary for it. So after the crimp ring was developed and we stamped it, we then needed to crimp it on. So we were playing with different crimp shapes and getting them to the point where we were happy with the contact that we were getting and the retention forces that we were getting. But the beauty of the mantle machine was we were able to use an existing die base, print it out of actual steel, and we didn't have to do any finishing because we had the tapped holes in the die base. We were able to print the holes right on the mantle machine that were just through holes to hold it down, and we didn't need to tie up a tool room. It allowed my engineering team to make the steel that they needed by themselves without tying up a toolmaker. So it helped us accelerate the time for the R&D to make sure that this product is functional before we get ready to release it. This is a sweep connector that we had, and we had a piece of tooling that broke. We call it a banana core because of the shape of it, but it's basically a rotational core that opens, as the mold opens, it rotates out of the part. Original core broke during production. We decided to attempt to print it on mantle. It printed in about 3 days. We did, again, H13 tool steel. Everything that we've been running has been in the H13. And we saved probably 75% of cost and at least 4 weeks of time to get this somewhat complicated shape completed. Plus, we were able to produce it in-house. We would have otherwise sent it outside to have it completed and made. This is a custom part for a specific customer. We were able to eliminate all of you can see all the ribbing in the tool, and it's fairly deep ribbing. Some of this goes down 1.25 inches. So we were able to eliminate all of that extensive EDM work that we would have had to do on this, as well as this has a step parting line where it's got a 15-degree main parting line, and then it steps to a flat and then a squared off flat at the top. So it made it it would make it a much more challenging conventional tool to be made. The mantle machine didn't really care. It just prints it as you have your model. This was again printed in H13 and probably saved somewhere between 40 and 60 hours of sync or EDM time. Minimal finishing afterwards. We did a quick grind on all the surfaces. We tapped the holes and it wired the ejector pins.
Awesome. Thanks, Bill. And like I mentioned earlier, I think pretty common theme there of removing EDM involved, removing the amount of toolmaker time, the amount of steps involved, and getting to something that is nearly finished and just needs a couple hours of grinding and tapping holes to get you there. And obviously a lot of value in doing that versus the design of electrodes, the machining of electrodes, the burning itself, the programming, etc. Removing all those steps.
I have a few other blocks too. This is a full stack of blocks that's making a PCB support. That was a custom, had 2 different custom arrows on it. So we did this real quickly within the mantle. This is that's a full mantle tool. That was a part run off of the tool. We were trying some quick quarter turn style for T-slots. So we were able to quickly print cavities and then run parts off of it. It makes it very nice and easy for doing quick changes or making a small modification to an insert and trialing it, and then having the ability to update your production tooling very quickly.
You don't have to answer this if you don't want to, but do you know roughly how many tools you've printed so far since you've had the machine here, which has been what, eight months now?
Yeah, we've had about 8 months. I can tell you that since we started I can't tell you the exact number of tools because I really don't know. But I can tell you since we first started and got used to the machine since January, so we had it about a month, maybe 5 weeks before we felt comfortable to really load it up. But since we felt comfortable, we have about a constant rotating 2-week backlog on the machine, and it prints probably, I would say, 80% of its time. And that's overnight and everything else. So what'll happen is if a job finishes up, the longest it usually sits before the next job is running is, unless it's not over a weekend, which we try to schedule it so it doesn't happen that way, but it's usually about 12 to 14 hours. So if it ends at night, they got to get the job out, get the next job loaded the next morning. Might be down for 12 or 14 hours, but other than that, we're pretty much printing all the time.
Yeah, it's great. It's awesome. Some great applications. I just wanted to share a couple more applications that I thought would be relevant that are not necessarily from Heyco. This is one from our customer, Westminster Tool, who is they're a mold maker mostly, so they're not a molder or an OEM. They're specializing in just building tools for their customers. They had a large medical device OEM bring them a part that they were trying to bring to market, and they were hoping to validate that part as soon as possible. They also wanted to do some material compatibility testing, so they wanted to run a couple different materials, and they wanted to do this in steel. This was really, really important for the medical device world, and we really see this for all of our customers, is that the value of running parts in a steel tool that's equivalent to production versus aluminum is really valuable, because the parts are going to mold so much differently in aluminum because of the thermal properties. That sure, you can get an aluminum tool quickly and inexpensively, but it doesn't give you much learnings about the actual production tool and the production process, and leads to some risk there. This is especially true, we find, on the medical device side. It was a really, really complex part. Unfortunately, we couldn't show the actual part because it was confidential, but this is a representation of it. It had over 40 swipe by shutoffs, so really, really, really complex part. When they actually tested this, the owner of the company said, "There's no way that's going to work. Like, you're wasting your time." And I don't think I'd be sharing it if it didn't work, but it did, luckily. It was 2 relatively larger inserts, so they printed these in about 6 days. What's really important here, though, is that it was only 2 hours of their actual team's time to get this started, to get the machine set up and running. It's going to print, hopefully, while you're sitting on the beach on the weekends, and it's back at the shop working. They put it in the furnace for about a day and a half, so they had these inserts completed in about a week. Then they did about 2.5 weeks of finishing work on these inserts. They are medical, very precise inserts, so they did some finishing work here. They squared up the blocks. They did some hard milling on the primary vents to ensure it vented properly. They did the wire EDM on the ejector pins. They tapped the water lines and bolt holes, and then just a couple of the swipe by areas they did hard milling to ensure that the tool shut off correctly. The result, they were able to deliver to their customer production representative molded plastic parts in just 4 weeks, which their customer was ecstatic with. They reduced the lead time by 50%. They estimated they would have taken about 8 weeks to build this tool traditionally, and they saved 65% of the toolmaker manufacturing time to produce this, which was really important for them because it meant their toolmakers could spend time working on other things while the machine was printing, and they just had to do a little bit of finishing. They molded over 7,000 pieces across ABS and a PC ABS blend. One thing that's not here, but it was really, really important to them, was this actually allowed them to win the production tool. So they are moving on to a full production tool that will be built traditionally, just because that was what the customer was most comfortable with, since it's going to be a medical device that is really, really valuable. But they would never have won that job if they weren't able to produce these prototype tools for them in just 4 weeks, engage with the customer, win their business, and then ultimately move on to a much more expensive tool in the production format that they're currently building now. Another example here from the medical world. This is actually from another large medical OEM who has a few of our systems, but molding in acetal and radel, which are some pretty nasty materials. Radel molds at really high pressure as well as high melt temperature, and acetal actually produces this corrosive gas, which it leads to some challenges. Again, this was a prototyping here, and they were doing some late stage trials, so they needed to be molding these parts inside of a steel tool rather than an aluminum tool. So it was really important for it to be in an H13 tool. Printed these 2 inserts you're seeing here in 62 hours, so about 2.5 days, in the furnace for a day and a half. They did 24 hours of finishing, just adding the ejector pins, tapping the mounting holes, and grinding it to fit into the mold base that you're seeing above. They didn't do any finishing to the actual feature detail, and they got that sort of matte EDM style finish that you're seeing on the part here. They were able to produce these inserts in just 8 days from design through production here. They also estimated that it would have taken them 122 hours of fabrication traditionally to build these of toolmaker time, but they were able to do it in just 24. I don't know how well, again, this will come across on the screen, but this is just an example of a part, and I guess Bill showed a bunch too, but you sort of get this sort of matte surface finish on the tool, or on the molded parts, which is great for many applications. If you needed better than that, a shinier finish or something like that, of course, you could go ahead and polish the tool, but for matte, it's totally fine for many applications. So they estimated also that they would have had to go out of house to do this, so 7 weeks down to 8 days, 50% cost reduction, and all of the features were accurate within a thou as printed. And like we looked at earlier, just eliminated almost all of those operations that were required to build this tool traditionally and dramatically helped them accelerate their time to market. One more sort of medical device application here. This is these are actually 4 slide nose components that are used to make this, this component that you're seeing on top. I don't actually know what the component is. That medical device companies usually keep their cards pretty close to their chest, which is totally okay. But they were able to tell us they reduced the lead time on these slides from 12 weeks down to 4 weeks and reduced the tooling cost from $63,000 down to $21,000. So a pretty substantial savings there. And again, all of the slides were accurate within a thou as printed, so they didn't have to do any finishing to that feature detail, which is really where the value is and really where they're hoping to eliminate and save some time. One last example here from our customer, Nicolay Plastics, who is a injection molder. So they are primarily a molder working with OEMs and other customers to mold parts for them. This is actually a latching component that goes onto a mounting system that goes onto the dashboard of an emergency vehicle, like a police car, to help them mount their laptop to the dashboard. So when you see them going 80 miles an hour in the left lane typing on their computer, this is the latch that helps them keep that computer tied to their dashboard. A lot of EDM involved in this part. You can see all the really, really small ribs. I actually have one with me here. A ton of little ribs in here, again, making it a really great application because all of the EDM that would be involved to produce this, they were able to eliminate, reduce the lead time from 6 weeks down to 2 weeks, the amount of operation time to just 12 hours from 180 because they were able to remove all of that time. And then this was molding a glass-filled nylon, so relatively abrasive material, but the H13 had no problem with this material. Again, just looking at all the steps involved here, really, really eliminating most of the steps to go straight from printing down to just that final finishing steps, which allows you to pretty dramatically reduce that lead time. With that, we'll sort of wrap it up here. Thank you for coming, everyone. I hope this was valuable and hopefully this was useful for you. We're more than happy to take any questions at this point and answer anything, but thanks again, everyone, for coming and giving us 45 minutes of your day today, and hopefully you learned something and hopefully this was valuable for you. And thanks to you, Bill, for being here.
Thank you for having me.
Awesome.
Thanks very much, Ethan and Bill, for the presentation. As Ethan just mentioned, we'll dive into some Q&A. I can see that some questions have already been submitted. As a reminder, if you haven't had a chance to submit your question, please do so now using the Q&A box. And why don't we start with a pretty straightforward one? What CAM program is required for the system?
Yeah, that's a great question. So as you probably saw, the mantle system looks very much like a traditional CNC machine because it is, that's been retrofitted. Fortunately, our software removes all the need for doing any CAM programming. All you have to do is select a couple settings and it's going to generate all the tool pathing for you. So you don't have to be a CAM expert. Myself, having very, very little machining experience and no CAM experience, can produce a tool like this with 20 minutes of my time and setting it up on the printer, which is pretty incredible to think about. So there is actually, there's CAM involved, of course, but we're taking care of all of that for you. Bill, I don't know if you have anything to add here, but how your team has, used the software and I think picked it up pretty quickly just because we really make it pretty simple and automated.
Yes, absolutely. It is. It does a lot of the work for you. Right now, all the engineers are using the software and getting the program ready for the machine. So none of my engineers had run CNCs before, and they can all run it without a problem. It's not a big issue. We do have a toolmaker that is also part of the team that does most of the setup of the machine and that kind of stuff, but it could be done by pretty much anybody that has mechanical ability.
Yeah, I like to say that I could probably teach anyone on this call how to start a mantle machine in an hour here if we were together in front of a machine. It's really that simple, and it's pretty crazy to think that you can get, be able to then produce this, which would take maybe years of machining training to be able to do something like this, but you can do it in probably just an hour.
Great. And I'm guessing you probably anticipated this question. How much does the system cost?
Yeah, sure. So we're pretty upfront with our pricing, mostly because people hear metal 3D printing, they think of $1 million aerospace systems and things like that. Our system all in is roughly $350,000. So pretty equivalent to a high-end EDM machine or a high-end CNC machine that most tool makers or most tool rooms are used to buying. So it's designed to sit right next to your traditional equipment. It's priced similarly. We knew that $1 million systems are not an option for most tool makers and molders and manufacturers. So it's $350,000, but it's priced to be competitive with equipment that you're used to buying. That was the goal, at least.
Okay. And Bill, I'm guessing this question is for you. I saw that you have experience with other metal 3D printers. What does Mantle do differently?
The largest difference that we see with is the finishes, the surface finishes. We're able to use the Mantle prints basically right off for all of the cavity detail without having to do any touching of those cavity details. So that's really the largest difference. There is a bit of a speed difference as well, that the Mantle machine seems to be a lot faster print-wise than some of the other technologies that I've been involved with. So yeah, those are the two big differences.
Great. And I think this may have come up in the presentation, but maybe you can elaborate on it. Can you polish the material?
Yeah, sure, absolutely. And yes, the answer is absolutely. You can polish the material. We say that you can polish to an A2. We'd like to think you can get to an A1. I'm not sure we've even tried to get to an A1 for like a lens or a clear component, but from what I've been told, you like look at an A1 finish the wrong way, all of a sudden it becomes an A2 just because of how precise those surfaces are. But we've been able to polish to an A2, and a lot of our customers have. So if you need to improve the surface finish, you absolutely can. What comes off of our printer is a D2, so it's similar to a Sinker EDM finish. It's kind of a matte finish that, like we showed today, is going to give you that sort of matte part finish, which for most of our customers is totally fine. But a lot of them want to know that if you needed to, you absolutely can go ahead and polish these inserts.
Great. And a question, maybe you can both field this one. Can you talk about the learning curve for bringing the Mantle machine into your tool room operations?
I can start. Yeah, sure. So initially, as everybody knows, there is a learning curve with new technology. And once the learning curve was very quick with the Mantle. As I said, we had it placed, and within less than a month, we were already loading it with jobs. So that's a very quick learning curve from that perspective. Really, the biggest hurdle is getting that first initial fear away and just going for it and trying it. So the learning curve, once you get out of your own way, it's not hard to learn at all. It's very quick.
Yeah, just to add to that, I'd say the biggest learning curve we tend to see with our customers is not how to use the technology. It's more of how do I design it for what needs to happen afterwards? Do I need to add 5 thou stock here because I'm going to want to grind it? What size do I want my ejector pin hole to be so I can get a wire in there and do it? Do I want to print that hole at all, or do I just want to drill it afterwards? And understanding how do they optimize the design for as little post-processing as possible, but for enough that they can achieve what they want to achieve. There's definitely seen some customers where they print initially and it comes out a little small and they have to go weld it, and they're like, we're never doing that again. We want to add a little material. It's much easier to grind a thou off than go back and weld a thou back on and grind it. So there's little learning curves of understanding what is the surface finish and tolerance you do need, what's the machine capable of producing, and what do I need to do afterwards? And once you can answer those questions, it comes together pretty quickly for a lot of our customers.
And as I said before, as you're in that process, Mantle is a great partner. They answer any question, and they're there to support you every step of the way.
Great. Well, thank you to everyone for your questions, and Bill and Ethan for your answers. Any questions that we didn't get to, we can follow up via email. Again, oh, wait, we got one more question coming in just now. What is an average part cost, and what are the contributions to that cost?
Sure. So I can answer it from like one of the generic samples I have here on my desk. This is another medical kind of mold insert that is probably, I don't know, 4 by 3-ish, or about the size of a dollar bill-ish. An insert like this would cost you about $900 all in. And what contributes to the cost, of course, is the paste material. We sell the paste in tubes that are a liter. It's $675 per liter or something like that. Most people don't really understand what a liter of paste is. So a part like this would take 3/4 or half a tube. So it would be a couple $100 worth of material. But of course, we're amortizing the machine as well. So we amortize at a 7-year lifetime. So there's depreciation over the print time. And really what drives most of our print time and costs is actually height of a part. Because every single layer has to be printed, dried, machined, there's time involved there. So a lot of our customers are trying to print things as thin as possible to get the cost down, to get the time down. And then if they need to, they can bolt it to a plate or put in spacers and things like that to really optimize the print time. So we have a pretty sophisticated cost model. So if you ever want to see the costing and throughput and print times of your own inserts, we can certainly connect afterwards and I can run that for you. But usually something like this would be about $800, but of course it also depends on how much finishing would need to be required at the end. But normally our customers are pretty happy with the part costs as well as the print times and throughput times.
Okay, great. Well, thanks very much, and thanks for getting that last question in under the wire.
No worries.
Any other questions that we didn't get to, we can follow up via email. And remember, if you're watching on demand, you can still feel free to ask questions as well. If you enjoyed the webinar and you want to share it, as a reminder, it will be available on engineering.com, and you'll also receive a link in your email that you can forward to someone you know who would enjoy the webinar as well. Thanks again to Ethan and Bill, and to Mantle and Heyco for sponsoring this webinar, and to all of you for attending. We hope to see you again at another engineering.com webinar. Take care, everyone.
Thanks, everyone.
Thank you.